everybody. This is going to be the 5th lesson on abstract algebra. Today we're going to be talking about equivalence relations and classes, applying that to orbits. Then we're going to be talking about the definition of a coset and proving Lagrange's theorem. So a quick note is that, like, in general, if you haven't heard of an equivalence relation before, it's a good thing. Equivalence relations, which I'm just going to call E.R because it's kind of long to say the whole name, are just good to know for higher level math in general. So even if they might not seem immediately relevant to group theory, maybe you might think, okay, this is good to know for higher level math classes like topology. You'll also need to know what equivalence relation is. But luckily they do have good applications to group theory as well. So let's go into the definition of an equivalence relation. A binary relation, which I'm going to call this little squiggle, on a set X is an equivalence relation if the following properties hold for all, let's say, x, y, and z and x. I'm just going to use these variables to help define these properties of the equivalence relation. We first have that x is equivalent to y under this relation. This is usually called the reflexive property or reflexivity. Reflexive. The second property is x is equivalent to y if and only if y is equivalent to x. This is usually called the symmetry property. And then finally the third one is that if x is equivalent to y and y is equivalent to z, then x is equivalent to z. And this is usually called transitivity, because it's like taking one claim and another and then being able to say something about both of them in a certain way. So you can kind of imagine an equivalence relation is a way of comparing two elements of a set and seeing if they're equivalent under some definition you give. We'll come up with a better way of understanding them eventually, but this is just the definition we're going to start out with. Okay, another definition. We're going to find something called an equivalence class. So let's let x, this be an equivalence relation. And really just this little squiggle is an equivalence relation, but I'm just going to write this just saying that the equivalence relation is on the set X. Okay. For all elements x and x, let this, we'll denote it by these square brackets, be all those elements y and x, such that y is equivalent to x. And we're going to call this the equivalence class. Equivalence class of x. So you can kind of imagine this as like, I mean, by definition, all those elements which are equivalent to x in the big set X. So I think the best way to understand equivalence relations and equivalence classes is just by doing a quick and easy example. So let's consider when x equals the set n, and in case you define the natural numbers without the number 0, I'm just going to union 0 on there. Sometimes there's a difference between if you learn math in the UK or in Europe versus in America. They have slightly different definitions for what a natural number is. Okay, now I'm going to define my equivalence relation. So I'm going to say n is equivalent to m if and only if n equals m mod 3. Okay? And if you don't know what mod is, it's basically like what is the remainder when you divide by 3. So 16 mod 3 is 1 because you get 15, is less than 16, and then you have 1 extra. And then like 6 mod 3 is 0 because 6 is divisible by 3. So let's examine some of the equivalence classes. Let's look at the equivalence class of 0. So this is going to be all those elements which are 0 mod 3. Well, I have 0, 3, 6, 9, 12, so on and so forth. Also, you're just going to have to believe me, this is actually an equivalence relation. You can check it for yourself. We already see we have the reflexivity property, since if you have something here that you're taking the equivalence class of, it's got to be in there as well, so x is equivalent to x. Let's look at the equivalence class of 1. This is going to be all those elements which are 1 mod 3. So we have 1, we also got 4, 7, 10, okay, so on and so forth. And we'll check one more. We got 2, all those elements which are 2 mod 3. So I have 2, 5, 8, 11, 14, and so on and so forth. Okay, cool. So something you might notice is if I went one further, let's say I looked at the equivalence class of 3, well, those are all those numbers which are 3 mod 3, which is just 0 mod 3, which would just get me back to the 0 over here. In fact, I'd just get 0, 3, 6, 9, 12, so on and so forth. And if I want to check the equivalence class of 4, it's going to be the same as 1. And if I want to check the equivalence class of 5, it's going to be the same as the equivalence class of 2. So you might notice that actually these sets, these equivalence classes, kind of group the natural numbers in a way. So if I drew out the natural numbers like this, so on and so forth, I could group all the ones in the 0 equivalence class. I'll just denote that by doing a red line under them. There's also 9 over here. I'll give blue for all the ones in the 1 equivalent class. And then maybe yellow for all the ones in the 2 equivalent class. And you see that basically this is going to group all the natural numbers together. It's going to form what's called a partition of them. So any natural number is only in one of these sets. If you're 0 mod 3, you're going to be in the 0 equivalence class. 1 mod 3, you're going to be in blue. 2 mod 3, you're going to be yellow. And so basically, we can just define all of the natural numbers in a way by splitting them up by their equivalence class. So n is really just, or I guess 0 union n, is really just the equivalence class of 0 union the equivalence class of 1 union the equivalence class of 2. Okay. Let's see if we can extend that idea. To prove that, we're going to work up to a little bit with some lemmas. And we're going to talk generally about equivalence relations now. Not by a specific example. Okay. So let's let x, comma, squiggle be an equivalence relation. And the lemma is if x, y, and x equivalent to y, then the equivalence class of x equals the equivalence class of y. Okay, hopefully this should be somewhat obvious, but let's check it. Okay, let's examine the equivalence class of x. Well, this is all those z in x, such that I didn't use y because we already have y defined. Z in x such that z is equivalent to x. But by our transitivity property, if z is equivalent to x and x is equivalent to y, then z is equivalent to y. So that means all those z in here are not only equivalent to x, they're also equivalent to y. So the equivalence class of x is actually a subset of the equivalence class of y. I could do this the other way around. If I look at the equivalence class of y, this is all those z and x, such that z is equivalent to y. But since by symmetry, if x is equivalent to y, then y is equivalent to x. So if z is equivalent to y equivalent to x, then I have z equivalent to x. So I get that actually y is also a subset of the equivalence of the class of x. But since I have both of these directions here, that just means the equivalence class of x equals the equivalence class of y, as desired. Okay. So now let's prove an important theorem. Let x comma squiggle be an equivalence relation. Then for all x comma y and x, if the equivalence class of x has some element it shares with the equivalence class of y, so that just means they're not equal to the empty set, then equivalence class of x equals the equivalence class of y. Okay, let's prove this. Should be pretty straightforward with the lemma we have. Okay. This should not be immediately obvious as well. This is just saying, like, if there's anything in common, they actually have to be the exact same thing. Okay, so let's let z be an element of the equivalence class of x intersect the equivalence class of y. Let me rewrite that. Okay. Then we get that z is equivalent to x and z is equivalent to y. So what I'm going to do is I'm going to swap this one around. We know this also means that x is equivalent to z by symmetry. But by transitivity, if x is equivalent to z and z is equivalent to y, then x is equivalent to y. But by our lemma, then we get that the equivalence class of x must equal the equivalence class of y as desired. Okay, proof over. So basically, this is saying equivalence classes are either disjoint, so they got nothing in common, or they're completely equal to each other. So you either have things like for the natural numbers, either you have the equivalence class of 0 and 1, which are completely disjoint, or you have like 0 and 3, and they have to be completely equal to each other. What this means is what we desired, really. A corollary is that the union, or really I should say the set of equivalence classes forms a partition of X for your set in general. And this is just because if you have, any two equivalence classes, a partition basically requires that you split all the elements into some of these sets and they can't have any intersection, which is basically what we're saying here. And I really think that this is the best way to think about equivalence relations. Because equivalence relation is basically just a way of taking a set X, which I'm going to draw by this blob, and grouping it up, basically just splitting it into parts here and calling each of these equivalence classes. And then you imagine any elements in these equivalent classes are just equal to each other by the equivalence relation. Okay. So the question is, why the hell are we studying this? Well, it's because we can apply it to things we have learned recently, like orbits. So let's prove an interesting theorem here, which is going to say that basically orbits can form an equivalence relation. So if the group G acts on a set X, then the orbits of X form an equivalence relation. Should have used ER. More specifically, X is equivalent to Y if and only if X is in the orbit of Y. Okay, let's prove this. So first we're going to prove, we need to prove three properties to know we have a relation. The first one is reflexivity. So we need to show that X is equivalent to X. Okay. Well, pretty clearly, X must be in the orbit of X, since we get that 1 dot X, which equals X, is in the orbit of X. Since, remember, the orbit is all those elements G dot X for any group element in G, and the identity is in G. So, of course, X has to be an O of X. And this just implies that X is equivalent to X by our definition. Now let's do symmetry, which is X equivalent to Y if and only if Y equivalent to X. So what we see is if X is an O of Y, well, this is true if and only if X equals G dot Y for some G and G. But this is true if and only if G inverse dot X equals Y. And you see I just multiply both sides by G inverse. And this is true if and only if Y is an O of X. And so I just basically use a chain of equivalences to get from X is equivalent to Y to Y is equivalent to X. Of course, you could do this without the if and only ifs and then just go the other direction, but it's a little bit faster to just do it like this. You might as well. Okay, finally we need to prove transitivity. So if X is equivalent to Y and Y is equivalent to Z, then we get X equals G dot Y and Y equals H dot Z for some G and H in G. Okay? This is just the definition because we know X is in the orbit of Y and Y is in the orbit of Z, and this is just kind of what that means. You know, if you're in the orbit, then you're some element G dot Y and you're some element H dot Z. Okay. But we can combine these. We can say X is G dot Y, and if I rewrite Y as G dot H dot Z, and then use our group action law to move the parentheses, G dot H dot Z, well, since G dot H is just another element of the group, this is just in G, then that means X is just in the orbit of Z, or X is equivalent to Z, which proves transitivity by our equivalence relation rules. Thus, orbits form an equivalence relation as desired. And of course, you should just note that in this equivalence relation, the equivalence class of X is just the orbit of X. So hopefully this should give you an idea of why I introduced the subject of equivalence relations. They might seem a little bit more relevant now. So let me just prove a quick question that I asked at the end of the last episode, which you can now prove pretty easily. If G acts on X, then orbits are either disjoint or equal. or equal. And now this is pretty obvious. I mean, the proof is just, of course, what we just said, that the equivalence classes of X are just the orbits. So if we have the fact that if like O of X intersect O of Y doesn't equal the empty set, well, this is just basically the same as saying the equivalence class of X and the equivalence class of Y doesn't equal the empty set. But we know that this implies that the equivalence class of X equals the equivalence class of Y. Okay. So now let's try to apply this idea that the orbits form an equivalence class and thus partition the set. And if we want to apply this, the idea is we want to find a relevant group action that can apply to really any group. And the way we're going to do this is we're going to define a group action that involves subgroups. Okay. We're going to consider subgroups in any group G and a group action that implies H acting on G. Okay. Theorem. Let H be a subgroup of G. Then H acts on the entire group G by left multiplication, namely H acting on G just equals HG. Okay, let's prove this. It should be, well, okay. And for the proof of this, just try this on your own. It should be pretty quick. And very similar to when we proved that regular left multiplication is a group action. It's basically the same. Okay, so a question is, what are the orbits of elements G and G? So take a second to think about this. Well, our answer is that they're going to look like sets like this. They look like sets HG. I'm going to denote it like this, which is the set HG for all H in H. So remember, an orbit is like taking an element in G and multiplying all of the elements in H by that element G, seeing where it goes. And we're going to note that by capital HG. Which is kind of like saying the set G, or sorry, the set H times G. And this happens to be a very important idea in abstract algebra, so important that they get their own name. Let's call these the right cosets. And I'll explain why I'm seeing right here. The right cosets of H is a subgroup of G, are the orbits of G and G by the group action H and G as we just defined by left multiplication. Okay? And we're, basically another way of understanding them are the sets HG, which is just equivalent to the orbit of G. And I'm calling this the right cosets because you multiply by G on the right. There's also an equivalent definition of left cosets where you multiply by G on the left, which I'm going to define at the end as an exercise. Okay, so a quick corollary of this definition is that the right cosets of H as a subgroup of G must form a partition. A partition of G. This is clear from all that we've just proved because the right cosets are orbits, which form an equivalence relation. So they have to form a partition of our set, which we're thinking of as G here. In particular, G is the union of some HGI these are the right cosets for, like I equals 1 to n for some n and n. Basically what I'm saying is that it's like hg1 union hg2 union hg3 union so on and so forth hgn. And so basically there's a certain amount of group elements, and you take the right cosets of them, or the orbits, and they partition all of G. The same way with the natural numbers, I could think of G1, G2, G3 as like 0, 1, and 2. And the union of all of those was a full partition of the set G, or the group G in this case. Okay, let's do another quick example to get a better understanding of this. So let's let G be equal to Z mod 12. And I'm going to think of this as the set 0 to 11. And H be the subgroup Z mod 3, which I'm going to think of as 0, 4, 8. Okay. So cosets here are going to be, once again, the orbit of the action of H acting on G, which in this case is H dot G is H plus G, because in Z mod 12 and Z mod 3, the action is just adding numbers mod 12. Okay, so if I wanted to find the coset H plus 0, which I can think of as the equivalence relation of 0, well, this is just adding nothing, of course. I'm just going to get H back. If I want to find H plus 1, well, this is just adding 1 to every element. I get 1, 5, 9. H plus 2 equals 2, 6, 10. H plus 3 equals 3, 7, 11. And you see if I do H plus 4, I'm going to get H plus 0 again. Okay. So these four cosets form a partition of G. In fact, G equals the union H plus 0, union H plus 1, union H plus 2, union H plus 3. Let me just write parentheses around here to make that make more sense. 0. Okay, because I get 0, 4, 8, 1, 5, 9, 2, 6, 10, 3, 7, 11. If I wanted, let's say, 8, it's in this one. 7, it's in this one. So there's always a coset that contains one of the elements of G, or Z mod 12 in this case. Now one might ask, we saw that we kind of got 4 cosets here. One might ask, okay, can I generalize, like, how many cosets should I get in general? Because it's a helpful way of understanding how the group breaks down according to a subgroup. It's important enough that it gets another definition. So let G colon H, with these little brackets, denote the index of H as a subgroup of G, or the number, I'm using hashtag as number because I don't want to write it out, of distinct right cosets. Of the form HG in G. So in this case, above, we had like when G equals Z mod 12 and H equals Z mod 3, the index of G and H was equal to 4 because we had 4 distinct right cosets. Now, something you might notice is that all those cosets had the same size. They had 3 elements. So basically for all G and G, we saw that the size of the coset was 3, which was also the same size as H. You also then might notice if you're summing H, or the size of H 4 times, and you get the whole size of the group, well, this is kind of like saying the size of the group equals the size of this index times the size of h, because you're adding the number 3 4 times. There's 4 cosets. Each coset has size 3. So 4 times 3 is 12, which is the size of z mod 12. This is a good observation. Let's see if it's true in general. So let's just prove a quick lemma first, which is that the size of the right coset is the same as the size of the subgroup. Okay. Proof. So, I mean, of course, we get like the size of this coset has to be at least less than or equal to the size of h, because in a sense you're basically multiplying g by h different elements. But the question is, are any of them the same? So you might get, multiplying by h by g gets you the same element, and then you would have less than h in size. So we're going to prove that all the elements are distinct to make so this becomes just equal. Okay. So let's let h1 times g and h2 times g and hg, and assume that h1g equals h2g, okay? But if I multiply by the right on g inverse, this just implies that h1 equals h2. Which means if any of the elements in the set are equivalent, well, I just was multiplying by the same element, h. So if there's h distinct element, size of h distinct elements, then the size of hg has to just be equal to the size of h. I'm basically creating h different size of h different elements. Doesn't matter if I'm multiplying by g, just, there's still capital H different elements in there. Okay. Now we can finally prove basically the next main theorem, which is Lagrange's theorem. Okay. If g is finite, so I'm restricting this to finite groups, and a lot of the things I've proved thus far are really only the case for finite groups. You can go back and check yourself if there's any sneaky assumptions where I assume things were finite and not infinite. And H is a subgroup of G. Then the order of G equals the index of H and G times the order of H. Okay, let's prove this. It's going to be very quick. So let's let G be a partition or a union of these like HGI for I equals 1 to n. And in particular, this n is actually the index of H and G because there's n different cosets, right? Cosets. Okay, since they're all distinct, this means the order of G is the sum from I equals 1 to n of the order of HG. But the order of HG is just HGI. This is just the sum of I equals 1 to n of H by our lemma, which is just n times H. And since we showed n was G, the index of H, this is just the index of H times the order of H. Perfect. And kind of the thing you should get from this, which is one of the most used ideas, I mean, this is very helpful. If you have the size of H, you can figure out its index, the amount of cosets. If you have the amount of cosets, you can figure out the size of H just from the group. But another more applicable idea is that basically what's the same, since G is some number, some integer n, and I can basically factor it into two different numbers. What this means is that the order of a subgroup H and G must divide the order of the group. The order of the group. Quick proof. By Lagrange's theorem, we have that the order of G equals the index of H and G times the order of H. If I just divide by I get the order of G divided by the order of H equals the index of G and H, but we know this is just some natural number, so which means H has to divide G. And this ends up being like a very useful tool because, I mean, let's say you have a group of size 50. I know all my subgroups have to be like size 25, 10, 5, 2, 1, so on and so forth. So you can kind of characterize what subgroups look like in your big group. So let's do a quick application of this theorem. Consider the order of some group G is some prime number P. This is prime. Okay? So what Lagrange's theorem tells us is that the order of a subgroup, so like let H be a subgroup of G, then the order of the subgroup has to divide the order of the group. What this means is since P is prime, the order of the subgroup has to be 1 or P. So the only subgroups are the trivial subgroup, which is just the identity, or the entire group. Okay, I can make an even more interesting claim. Now, choose some G in G where G is not equal to the identity. And consider the subgroup H equals 1 comma G squared all the way to, like, you know, G to the order of G minus 1. We considered this subgroup at some point in an earlier video. Well, since G is not equal to 1, I know that, well, the identity is in this subgroup, and G is in this subgroup, and this is a subgroup of G. But we all know the only subgroups are 1 and G, so actually H has to equal the entire group G in this case. And that implies that the group G is cyclic. So we just proved that if a group has in the order of a prime number P, then G must be cyclic. Which is pretty cool. So if you ever see a group of size 5 or 13 or 17, you know it has to be cyclic. Okay, now I'm going to leave off with some exercises which you can work on your own. Okay. Using Lagrange's theorem, I want you to characterize the subgroups of Z mod n for any n and n. So think about how you would do this. What I mean by characterize is, say, if I give you any n, you can tell me exactly what subgroups Z mod n has. Think about what Lagrange's theorem tells you about what those subgroups can be, like what their size can be, and then check if those sizes are possible. Okay, 2. The left cosets of H as a subgroup of G are sets of the form GH in G. So right cosets were G multiplying on the right, left cosets are G multiplying on the left. And I want you to prove that basically there's the same number of left cosets as right cosets. That's same number of left and right cosets. And this should make the idea of the index a little bit more rigorous, because it's slightly arbitrary that I just define it to be the right cosets. You could just as equally define it to be the left cosets, and this exercise will prove to you that it's still okay to do so. You'll get the same number both ways. Okay? So third exercise is let G be a group element. This one should be pretty quick. Prove that the order of G has to divide the order of the whole group. So the order of some group element has to divide the order of the whole group. Then prove that, hopefully if you get that, this should be pretty quick, that any element G to the power of the size of G has to be the identity. Okay. And then last exercise, I want you to find a counter example, maybe by searching up or just figuring out on your own, to the converse of Lagrange's theorem. So what I mean by that is, basically, for example, if n, some number n, divides the order of a group G, then there exists a subgroup of G where the order of H equals n. And I want you to find a counterexample to this. It's not true. And there's many counterexamples out there. So, note that Lagrange's theorem only proved one direction. This direction is not true. If you have any number which divides the order of a group, there might not necessarily be a subgroup that has that size. Whereas if you have a subgroup, it has to divide the order of the group. Okay. Hopefully these exercises will be helpful for practicing Lagrange's theorem. Okay, thanks for watching.